Are they true circles? Okay, let's get started. Here we go. Ready to start. Here we go. All right, so last time we were looking at some circles here, and we said that we could take the radius. So don't just burn this image in your mind, right? Take the radius, which is the distance from the center of the circle out to the edge of the circle. We've took that a radius length. All right, we ready to start? Okay, so please stop talking, everybody. And so we took a radius length from the center of the circle out to the edge, and we wrapped it on the circle, and we said that that has a length 1, but it also is 1 radius length, right? So there's two ways to look at that. There's a length 1 and it's 1 radius length. So this radius has a length of what? This was 4, and we could take it and wrap it on its circle. So it has a length of 4, but we could also say it has radius length of still 1, right? So it's a 1 radius length, but now that is 4 axis units, right? 4 axis units. Radius length length of the radius equals 6 axis units. We could wrap it on its circle. How many radius lengths is it? Still 1 radius length. And we saw that 1 radius length always gives us the end of that radius length on the circle terminates along a line, and we call that the terminal side of the angle. So that we said the initial side of the angle we said was the positive x-axis, or we said the 3 o'clock position. The 3 o'clock position. And for the next month, we're going to talk about angles swept counterclockwise from the 3 o'clock position. So watch it, ready? Angles swept counterclockwise from the 3 o'clock position. So our initial side of the angle is the positive x-axis, or the 3 o'clock position. The terminal side of the angle, if you use 1 radius length, or any number of radius lengths, it always falls along a straight line. So they call that the terminal side. Okay? So again, this is going to be terminology we use. Angle swept counterclockwise from the 3 o'clock position. This is kind of the conventional standard angle in trigonometry. And so we said that 1 radius length always gives us the same fraction of a circumference, right? Because that terminal side, all those points where the arc ends fall along that same line. So this 1 radius length is the same fraction of any circle's circumference. So we said it was a valid way then of measuring angle. Using radius lengths along as arc lengths is a valid way to measure an angle. And so if the angle subtends, the rays of the angle cut off 1 radius length, then the measure of that angle is 1 radian. So what is 1 radian? An angle that has measure 1 radian has rays that subtend 1 radius length of arc length. No matter what size circle you pick, it's going to be 1 radius of arc length. So here is 2.9 radius lengths of arc length, no matter what circle you look at. 2.9 radius lengths of arc length are cut off by this angle. What's the measure of that angle then? 2.9 radius lengths are cut off by the rays of this angle. What's the measure of that angle? 2.9 radians. 2.9 radians. The radian angle measure is the number of radius lengths that the rays of the angle cut off. That's what radian measure is. Okay, so here is, let's go to 3. This is 3. So we have an angle swept counterclockwise in the 3 o'clock position. It sweeps out 3 radius lengths of arc length. Therefore, the angle is 3 radians. Okay, and so a common symbol that we use for this angle swept counterclockwise, or the measure of the angle swept counterclockwise, is theta. Okay. So this number, theta, is a number. Okay. It really has kind of 2 different aspects to it. It's a number of radius lengths of arc length cut off by the angle, but then it's also the measure of the angle, which is what do angles measure? What do we measure about an angle? Openness, right? So the arc length is 3 radius lengths. The openness is 3 radians. So, and theta can mean both. See, the arc length cut off, arc length subtended, equals 3, what's the unit for that? If it's the arc length subtended? Radius length, or radii, okay? That's like measuring distance around an arc. The openness of the angle what do we measure openness in? Radians. Radians is openness because it's angle measure. And what's the openness of this angle? 3 radians. So theta can take on both meanings. Theta can take on the meaning of openness in radians. So no, actually, that's the primary. So that's what theta is standing for. Okay. So theta is standing for the second one. Okay. Because theta is the measure of the angle. That's what theta means. But that numerical value of theta will always be the same as what? So that number, that's the openness in radians, is always the same as what number? Radii. Number of radius lengths, right? So you can shift back and forth between radians and radius lengths. Theta specifically means the openness of the angle in radians, but its numerical value is the same as it comes from. The numerical value comes from how many radius lengths. Okay, so I want you to make a table. So we've got purple, blue, red. And I want you to, there's going to be, so R stands for the radius, the length of the radius in axis units. The length of the radius in axis units, that's R. Theta, we just talked about. S is the length of the arc in axis units. So R equals the radius length in axis units. Theta we know, and S is the total arc length in axis units. So I want you to work with the person next to you. And for each one of these, the purple, the blue, and the red, you're going to determine all of these values. Do all three of those, R, theta, and S, all make sense? Do they all make sense? What they mean. So now determine each of those 9 numerical values, R, theta, and S. Go. Okay, here we go. So how about Derek? Tell me about the purple. What is R for purple? What's that? He wants 1. What is theta for the purple arc? 3. And what is S? He wants 1, 3, and 3. Agree? Okay. Nick, how about the blue?
R is
4. Yep.
Theta is 3.
Okay.
S is 12.
Agree with that? So why is theta still 3? It's longer arc, right? So why is it still 3? What's that?
It's in radians.
It's in radians?
Measuring the radians.
Measuring the radians. Danny?
The amount of openness is similar between all angles?
Yeah, it's the same, right? So the amount of openness is the same. And you could also say 3, also besides openness, you could say that number 3 is number of radius lengths, right? That's where we started. We started with radius lengths. So they all have the same number of radius lengths that define that angle. Okay, red. Let's see. How about Josh back there? Red.
R would be 6.
6.
And then theta would be 3 still.
3.
And then 18.
Agree with that? Okay, so we see a pattern emerging. How can we then relate R, theta, and S? How can we make a relationship of R, theta, and S? Matt wants to do that.
S equals theta R.
S equals theta R. Is that right? So what is R? R is, know how many axis units long the radius is. And S is how many axis units long the arc is. So why does it make sense that it would be theta times R equals S? So this is something more than just to memorize, but it should make perfect sense why that's true. Who could say why that's true? Adam.
Because theta is kind of easier to measure. It's based off radius.
So in this formula, theta is kind of representing what? Should in this formula, is it most useful to think of theta as the openness of an angle or number of radius lengths? To make sense of this formula. So R is how long one radius is, and then theta is how many you have, right? If you have a length of one radius, and you think of theta as the number of radius lengths, it makes perfect sense. You're going to take how many you have times the length of each one, and that'll give you the total length of the arc, right? So this is the length of one radius. The number of radii that you have. So in this case, we have 3 of whatever the radius length is. So if the radius length was 75, we take 3 lengths of 75, and that would make 225. This makes perfect sense. You got the length of one radius, and then theta is counting how many of those you have. And that will give you the total length. Should be easy, right? Multiplication. So even though, theta does mean openness, that's our primary meaning for it. In this equation, it really helps to think of that number theta as how many radius lengths are drawn out. Okay, any questions on that? So then we said last time, how many radius lengths does it take to get halfway around the circle? Yeah, something like more than 3. Closer to 3 than 4. And here, with here's 3.1 and here's 3.2. It's like pretty close to right between 3.1 and 3.2. And so exactly, so if I come in here and I say, I want n to equal 3.14159, which we know is a good approximation for pi, look where it ends. So I just set the number of radius lengths to be 3.14159, and that arc goes pretty close, very, very close to exactly halfway around. Why isn't it exact? Because pi is an infinite decimal, right? The numbers keep going and going and going. To get the exact number of radius lengths, you need all the decimal places of pi. But even if I zoom here, and just with 3.14159, I zoom in, 3.14159 is doing a pretty good job getting exactly halfway around. See that? So then let's look at, so this is 1 radius length, ends up here from the 3 o'clock position, 2 radius lengths, 3 radius lengths, we can keep going. Maybe? Oh, I gotta get rid of this now. Okay, so there, 3 is right before halfway, and then 4, 5 radius lengths. There's 6 radius lengths. And so how many radius lengths to get exactly all the way around the circle? 2 pi, right? Because it's 2 halves. So if pi is halfway, 2 pi must be a full circle. So here are the whole numbers of radius lengths, or whole numbers of, say, angle measure in radius lengths. So those are whole numbers of radians. 1, 2, 3, 4, 5, 6. So what do you notice about those places on the circle? So we've got whole numbers of radius lengths, which is those are nice numbers to work with. But what about these places on the circle? Are they nice and symmetric and even? And no, they're just they have no kind of association with how we could split it up nicely, right? So then we start with, if we have pi here, if this is pi radius length is exactly halfway around, this is pi, then how many radius lengths to the very top of the circle from the 3 o'clock position? Pi over 2. And what about, okay, so like 1.5 pi, right? 1.5 pi. So a full pi and then a half a pi, 1.5 pi. And then you said all the way around is? Okay, what about 1/8, an arc that's 1/8 of the circle's circumference? How many radians, how many radius lengths will give an angle that's, Devin, how many radius lengths will give an angle that's 1/8 of the circumference of the circle? What's that? I can't hear you. You don't have the answer. You don't know. Okay, Jacob. What's that? 1/4 pi, right? So 1/8 of the circle would be here, and that'd be half of pi. What about this symmetric angle here? And so these are the, what about that symmetric angle that splits that quadrant in half? This is half of pi, and this is a full pi. So this would be 3/4 of pi. All right, find that number. So if we want nice symmetric angles on the circle, then we need to have them be factors and fractions and multiples of pi, because we know halfway around is pi. So if we want these nice symmetric angles, we're going to have to use pi. But here's the problem. So after a while, you just look at these symbols and you think they mean a point, right? So you look at you say 3 pi over 4, oh, it's that point on the circle. No, it's not. Find the number 3 pi over 4 in your calculator. Find an approximation for 3 pi over 4. What is it?
2.35619.
2.3562. You said 19, right? Okay, so it's a number. It has meaning. So you can't lose the sight of when we start using these angle measures that use pi, you still are talking about a number. In this case, 3/4 pi is 2.3562. What does the number mean? What does that number mean? Mitchell.
It's the height from the x-axis.
The height from the x-axis. Agree with that? Benry, what does this number mean? 2.3562. What's that? How open the angle is, and where does that amount of openness come from? What is the 2.3562? I know Danny knows. Nicholas, what's the 2.3562? Arc length measured in what? Nope, arc length isn't measured in radians. Radians is openness. Length is measured in radius lengths. So it takes 2.3562 radius lengths to get to this point on the circle, and so therefore the amount of openness is 2.3562 radians. So if we want to write that exactly, we use 3/4 pi, but we can't lose sight that that is a number of radius lengths that corresponds to an amount of openness of the angle. Okay? So don't just start looking at these pi, these fractions of pi, these multiples of pi, and saying, oh, that's just the name of this spot on the circle, right? That's not what it is. It's a number. It's the number of radius lengths, giving us the amount of openness and radians. Because what? Here was 1 radius length. Here was 2 radius lengths. So 2.3562 radius lengths takes us to this nice symmetric halfway spot in what we call quadrant 2. So when we start from the 3 o'clock position and we sweep counterclockwise, we go through the quadrants. So the first quadrant we go through is the upper right. So that's quadrant 1. Next quadrant, as we sweep out angle, quadrant 2, and then quadrant 3, and quadrant 4. Okay, so I want you to sketch find the position of the terminal side of the angle for the following angle measures. 2.5 radians, 0.3 radians, 4.25, 6.1, -1, and -5 radians. So a negative angle measure means that you start from the same place, but you sweep clockwise. So you're going the opposite direction. You sweep clockwise is a negative angle. So find sketch these angles. Sketch all these angles. Okay, and stay on task. All right? You're not looking at a computer screen, except for this one. Jerome's going to make sure you're staying on task, okay? Okay, Ramy, how about 2.5 radians? Yeah. First of all, which quadrant? Second quadrant? A little more than 3/4 pi. We just did 3/4 pi, which was what, 2.3562, right? So it's going to be, exactly where is 2.5 radians? How could you describe exactly where it is? Right, it's going to be right here. Something like that. 2.5 radians. Okay, 0.3 radians. Tyler.
Just past the start.
Just past the start. So, like here? Yeah, so 3/10 of the way up to 1. Like that. That's 0.3. 3/10 of 1 radius length. Okay, 4.25. Tyler, this Tyler.
Quadrant 3.
Quadrant 3.
Just a little bit past the 4.
Yep, so here's 4, so we went another quarter radius length past 4. Something like that. There's your 4.25, swept from 3 o'clock. 6.1. Just 1/10 past. That's the best 6.1 angle I've drawn all day. All the way around to here. So the amount of openness is almost a whole circle, right? It's just the amount of openness is almost a whole full rotation. Okay, -1. John, so how would I do -1?
So it would be in the fourth quadrant,
Okay.
a little before the 6 reading.
Yeah, so we need this amount, this radius length, but going this way now, right? So wherever this lines up this way, could drop a vertical here, and that would give me my 1 radius length. And so swept clockwise from the 3 o'clock, that would be -1 radian. RAD is the abbreviation for radian. Okay, any questions on this? So radian angle measure comes from that number, that's that number of openness in radians, comes from what? Where do we get that number? That's the openness in radians. What's that? It's from the subtended arc length. What about that arc length? So where do we get that number? How many radius lengths, if we measure that arc length in radius lengths, that gives us the openness in radians. Okay, so 1 radian. Remember our original thought about angle was fraction of the circumference. So I want you to find that 1 radian arc length in terms of fraction of the circumference. 1 radian equals what? What percentage or what fraction of the circumference is 1 radian? How would you do it? Eric?
I did 1 divided by pi, and then got 0.318,
Okay.
and I divided that by 2,
Okay.
got 0.159.
Okay.
So 1 radian is 0.159 of 1.
So you did what fraction of a half it was, and you took half of that.
Yes.
So could we do this one? What fraction of the whole way around it was? What would that be? 1 over,
2 pi.
and you got 0.15. Give me
Yeah.
a little bit more.
159.
Okay. So that means that 1 radius length, or 1 radian, is what percent of a circular rotation? Right, so as a fraction, it's 0.159 of the full circle. As a percent, so these angles are the same. So if we could call the 15.91% angle, or the 0.1591 angle, is the same as 1 radian. It's the same amount of openness. So now, how can we use this fact to figure out how many degrees is the same amount of openness as 1 radian? And what would you do? Multiply what by 360? Yeah, you're going to take that fraction, the 0.1591, you're going to take that fraction of 360. And what do you get? 57.24 degrees has the same amount of openness as 1 radian of openness, or 0.1591 of a rotation of openness. So this is why we started off, or one reason we started off by looking at percent of the circle, or fraction of a circle, because if you can get the percent of the circle or the fraction of the circle, conversions are easy. You can convert to any system of measuring angle if you have the fraction of the circle. And you don't have to memorize any formulas. Some of you you've had formulas you memorized in the past that will get you from radians to degrees or degrees to radians. Those days are over. We're going to focus on fraction of a circle, and then there's nothing to memorize except for what a full rotation is in whatever unit you're using. Okay, so let's do some examples here. So we can just focus on, perfect, okay. So we looked at what? We said 1 radian was what percent of the circle? 15.19%. And then to find the corresponding number of degrees, we took 15.19% of 360. So we had, this was 1 radian. And what did we do? We found the same openness as a percent of the circle, 0.1519. And that was by 1 divided by 2 pi. What fraction of 2 pi is 1 radian? 0.1519. And then we took that and we said, oh, well, we're just going to take 0.1519 of 360. And we got 57.2 degrees. Is that right? Is it 0.2? 0.24 or 0.4?
0.24.
Okay, so let's just go with 0.2. Okay. So I want you to find how many radians, use this approach, find how many radians is 212 degrees. 212 degrees. So first of all, where is 212 degrees? Which quadrant? So this is 90, right? 180. What's this? 270, so 212. Something down here, right? So first you're going to find what percent of the circle that is. And then you're going to take that percent of what? A full rotation in radians. Take that same percentage of the full rotation in radians, and it'll give you the equivalent openness in radians. Nothing to memorize. Nothing to memorize. It just makes sense. Everything goes through percent of the circle. Okay, who's up? Are you going to report the answer? Or you have a question? I'm going to think out, so I'm hear from somebody else here. Newer, did you get this? So how would you do the first step? How would you get percent of the circle from 212? One? Yep, you're starting with 212 degrees. No, that's the way we're going to do that is by getting the percent of the circle that 212 is. How do we get the percent of a circle that 212 degrees is? Right. So we're gonna come here first, and we're gonna get 212 divided by 360. Anybody got that? 0.589. Right, so I'm rounding it to 0.89. So what percent of the circle is 212 degrees? 58.9%. And so now to get radians, we're going to here. Yeah, so we want that fraction of 2 pi. And what do we get? Go ahead. 3.7. 0? Okay, 3.70 radians is 212 degrees. Okay, gradients is another way of measuring angles. It's based on a full rotation is 400 gradients. So that's all you need to know to be able to convert to and from gradients. Okay? So how about 90 gradients? So 90 gradients, let's find that in degrees and radians. So 90 gradients. First of all, what quadrant will that be in? Okay, so here's 0. What will the top of the circle be in gradients? It'll be 100 gradients because it'll be 1/4 of a full rotation. So 90 is a little bit less like this. So that's 90 gradients. Or grads, 90 grads. So I want you to use this approach to find how many degrees 90 grads is and how many radians 90 grads is. So let's just make a guess. What percent of the circle would you guess it is? Estimate. Little less than 0.25, right? It's going to be a little less than a quarter. Anybody got it yet? 0.225? And then how would we get degree? Now we know what fraction of the circle it is. To get degrees, we would take that fraction of 360 or multiply by 360. To get radians, we would take that fraction of 2 pi. See, this is the best. This is the best way to convert angles. It's all goes back to percent of the circle, and then there's nothing to memorize.